Right, so this is section 2 of module 1 of instrumentation 2, temperature, pressure, level, and flow. Measuring pressure. So those, let me get the PowerPoint up here. The whole thing, like all of instrumentation, is about the measurement and manipulation of temperature, pressure, level, and flow. There's some other ones, but those are the main four that you deal with. Talking about pressure, I know I gave you a couple of these, but I'm going to go back over them. I've got the pressure highlighted in the trade terms, the amount of force given by a substance over a given unit of area. And then I have the equation right under it highlighted. So pressure equals force over area. On the right hand side of the page, I've got where you see gauge pressure highlighted in blue to the end of the paragraph. I've got that highlighted. Gauge pressure is measured and expressed as pounds per square inch gauge, or PSIG, or kilopascals gauge, and considers the presence of atmospheric pressure. For gauge pressure, the gauge starting point of 0 PSIG actually begins at the atmospheric pressure. So, what do we say atmospheric pressure is at sea level? 14.7. We are at sea level. So if we went out, you also need to have, the equation right after the next paragraph is also highlighted. PSIA, which is absolute pressure, is equal to gauge pressure plus atmospheric pressure. So if I had my tire gauge that I pulled out to go put on my tire outside, remember it's not connected to anything, it's reading 0, right? But that's gauge pressure. It's taking into account that there's already a pressure pushing down on us. We're about at sea level, so we're at 14.7. So our gauge pressure, our absolute pressure, PSIA, is equal to PSIG plus our atmospheric pressure. So if our gauge pressure is reading 0, then our PSIA is going to be 14.7. So on and so forth. At least for me, the hardest part about that is remembering how to separate absolute pressure and atmospheric pressure. So absolute is the combination of gauge and atmospheric. Atmospheric is just how much, because you have more pressure at higher altitudes, right? Less pressure?
Yeah, because like in Colorado, it's 12.2 or something like that.
Okay, less pressure. I listened to a pretty cool, Neil deGrasse Tyson does a pretty good explanation of like pressures and stuff like that. I think he's actually here this week. He's at the same But they were priced, it was like $200 a ticket. I also have the equation to find gauge pressure, which is just manipulating that equation around. So I got gauge pressure is equal to absolute pressure minus atmospheric pressure. Moving on to page 12 and 13. You can see this picture on the board, like we have, they have water in here. So pressure is equal to force over area. So water is the force. We know how much water weighs. It's about 8 pounds.
Per gallon?
It's per gallon. So per gallon, water is about 8 pounds. So however much in here, that's pushing down on the area. So pressure equals force over area. So 1 pound of force over 1 square inch equals 1 pound per square inch. And then 3 pounds over 1 square inch would be 3 pounds per square inch. Everybody go with that? Pressure, I don't have anything in pressure calculations, but I can see them pulling the equation. You're definitely going to have the problems about finding absolute and gauge pressure and stuff. Differential pressure 212. The first sentence, my first highlight. In some cases, it's necessary to measure the difference between pressures at two related points, called differential pressure. typically written as dP, d over P, or delta P, spoken as delta P. The Greek letter delta, or the triangle, means a change in the change as in the change in pressure. Everybody know that? Triangle represents a change. The immediate next sentence is an online test question. Define differential pressure, subtract the lower pressure reading from the higher pressure reading. Pressure measuring devices, manometers. These are something that I don't like. I've never used a manometer, but you can tell like how many inches of water and stuff like that you have.
Yeah, I just tried to set it up for you. It receives the jobs, but it will not print. When you get a chance, try to print to it. It should work.
It should work for P-Tech plotter. Alright, next chance I'll try something, I'll let you know.
We have two guesses. Either A, the wall port is a different VLAN, or two, that the card itself is destroyed.
Card
So
itself.
there's just a network interface. There's no way you plug the cable into it. If something's wrong with the NIC. But it receives the job, but will not print. But I just did a test page and it worked fine.
Yeah, I know it print, like I printed off their Halloween thing or whatever, so I know it prints. Alright, I'll try
It's printed, but it won't print when we send a page from our side. So we'll see if we can do it in yours. So you get a chance to send one.
We'll do it. I'll let you know what happens.
Appreciate it.
Thank you. Manometers. 221, first sentence of 221 is highlighted. The basic principle of operation of a manometer is that a column of liquid of a certain height exerts a specific amount of pressure. The immediate next sentence is a separate highlight. Liquids commonly used in manometers include mercury, water, and certain types of oil. Water, I think, is the most common. So manometer can just be hooked up, like this would be my pressure side. So however much pressure is put on here, I can read on my atmospheric side, and I can see what the difference in pressure is between the two. Pretty simple device. Flipping over to page 14 and 15, bellows type pressure sensors. 222. We've got the first sentence highlighted. A common type of pressure sensing device is a bellows type pressure sensor shown in figure 17. So that's what's on the board here. So you can see your applied pressure comes in the bottom. This is a bellows. So this is like a metal bellows that has like I don't know what to call those, but it expands and contracts based on pressure. Not a lot, just a little bit. So apply pressure here, pushes against the spring, changes the connecting link, and then the gear changes the scale to whatever it is. Bellows type pressure sensing device. 223 on page 14, a board-on tube. This is a lot. You'll see these quite a bit more. The first sentence is an online test question in 223. Board-on tubes are often used in pressure gauges and transmitters. How do they not show me a picture of a board-on? Let me give you one more highlight on board-on tubes, and then we'll flip over and take a look at them. Last paragraph on page 14, first two sentences are highlighted. Spiral and helical board-on tubes work on the same principle as the C-type. However, both of these types of board-on tubes produce more tip travel and higher torque capacity at the free end of the C-type. So if you flip over to page 16, you can see the board-on tubes. I can't believe they didn't give me a picture of one. They did in the next one. That's not it. It's not it.
Okay, this is like verbatim what a instrumentation class is.
It kind of, well, yeah, kind of, sort of. I mean, this is the stuff, especially for instrumentation 4 that y'all are getting. Let me spill that. So just looking at this picture that's on the board, have I talked about these at all? No, I haven't. Like I've taken the instrumentation classes, mixing in with what I've told y'all. So this would be a gauge like you would measure your tire pressure with, right? So pressure comes in the bottom here. This is a hollow metal tube. So as pressure is pushing here, like my hand is like the C of that board on tube. As I push pressure in the bottom of this, what's that C gonna want to do?
Go up.
Straighten out. And if I put like a crazy amount of pressure in there, it's gonna want to open, right? Because I'll push pressure in there. So as the D part of this moves upward, there's a linkage to a gear system that turns the dial. So still a pretty simple device. Some stuff you don't want to do. Obviously, you want to work within your pressure limits. Like if you over pressurize this, like everybody's taking a piece of metal and bend it, and then try to bend it back, and it doesn't have the elastic properties that it had before. So if you straighten this thing up, like if it starts as this, and you straighten it up too much, it's not going to come all the way back. And that's where you'll, like if you ever grab a gauge and it's not connected to anything and it's on like 5 psi, that's because somebody has either slammed pressure on it or it's been over pressurized. Right? So that's how a board on tube works. And you can kind of see that on page 16, like they show the motion. But you can also have the spiral or the helical board on tube. Same principle, just a different type of design. The C type, I think is the most, I don't know that that's the most common, but it's the most common that I've seen. Um, 230. Guess we're not in this. Conditions that damage pressure measuring instruments. The second sentence in 230 on page 16 is highlighted. 3 common causes of damage to pressure measuring instruments are overpressurization, temperature extremes, and excessive vibration. Page 17, second to last sentence of that first started paragraph is highlighted. The normal reading of a properly selected gauge should never exceed 75% of the scale value. So, like for heavier duty trucks, they get, like my truck gets 80 psi in every tire. And that's what I run in my tires. Huh?
It's a lot.
It's a lot, but it's a 1-ton truck.
Yes.
But that a lot of gauges only go up to like 60, because that covers the wide gamut of stuff. So if I put a 60 psi max gauge on that, it's gonna damage the pressure. But even if I had 100 psi gauge and I put it on and it's 80 pounds, that's over my 75% max. Not that it won't work; it'll still work. But you want to stay in between 25 and 75%. So I would rather have a gauge that goes up to like 120 to read the pressures on my tires, whereas like most cars are somewhere between like 28 and 36 for the most part. So having a gauge that only goes up to like 60 is fine. So it's a repeated like going to the extremes is what's gonna damage these over time. Everybody go with that? Flipping on to page 18 and 19. Protection of pressure gauges. 231, third paragraph, first sentence is highlighted. Pressure gauge isolators, figure 21 or what's on the board, are used to separate standard pressure gauges from hazardous or corrosive process fluids. So we have that metal C-shaped device that's on the inside of this gauge, right? If I wanted to measure pressure in acid lines, would I want to put hydrochloric acid up in that metal C-shaped board on tube? No. So what they do is they have separators here, so the pressure of that, if say it was acid, is coming in the bottom, and then there's it's not a bladder, it's a diaphragm. There's a diaphragm in the center of this that separates the acid from some type of inert liquid that actually is what pushes inside of this. So the acid pushes on the diaphragm pushes on whatever that liquid is, and that's what goes into my gauge. So that protects the gauge from coming in contact with something that could corrode. Page 19. First sentence on page 19 is highlighted. A snubber, figure 22, is installed at the input side of the pressure gauge to dampen the effects of multiple rapid pressure changes or pulsations at the input to the gauge. So that's just so somebody can't, if somebody slams pressure on to a hydraulic circuit or something like that, these gauges, the snubbers will dampen the effects of what's going into the gauge. Like, they're not going to act as quickly, but they're going to be protected from that pressure that's slamming onto it. Take a second and answer those 3 questions on page 20. All right, continuing on to section 3. Section 3, this is going to be measuring levels. So you can have different types of level, obviously different types of instrumentation that will measure level. You can use capacitance to measure level. I'm going to show you all how to do that in this chapter, how you turn a tank into a capacitor. I don't understand why they have conductivity whenever they say reference to one of them. You should know what head pressure and level and specific gravity all are. First paragraph on page 21, second sentence is highlighted. Level is often convertible to a volumetric measurement. So usually, like convertible to a volumetric measurement, like you could have a tank, and then you can say that tank holds 3 gallons. That's all they're saying. Direct level measurement. So you're going to have direct measurement and indirect measurement. So a direct measurement is saying you can only do direct measurements with level between the temperature, pressure, level, and flow. So a direct measurement is, I want to know how long this desk is. Take a tape measure, I can see how long this desk is. Anybody ever seen them check the levels of tanks at a gas station before they fill?
Take that like long pole.
They have a stick. Stick a stick all the way to the bottom of the tank, pull it up, see where it's wet. While that is a very rudimentary or crude way of measuring, it's pretty accurate. But that would be a direct measurement, because I can see the actual level of the tank. Good. Which is actually the second paragraph of 311. Got a little ahead of myself. Dipsticks and lead lines. It talks about checking the gas tanks for levels. I've got the second to last sentence in that second paragraph of 311 highlighted. Although this method of level measurement seems crude, it is accurate to about 0.1% with ranges up to about 20 feet. Out to the side of that, I wrote use to measure directly, using the stick. Another one would be like the dipstick in your car. You're measuring the level directly, essentially. Sight glasses are another way to measure directly. For y'all that have been working on the trainer right here out the door, there's a ruler or whatever on the outside of those level tanks. That's measuring it directly. Whenever you're supposed to keep it to like 5 inches, that's measuring it directly. The first 2 sentences on page 22 are an online test question. However, it is important to note that conditions inside the vessel can lead to inaccuracy. For example, when a steam boiler or burner is in operation, air bubbles form inside the boiler vessel, raising the level of water inside. So there can be some inaccuracies with doing this. Float and cable arrangements, 313, first sentence is highlighted. Float devices are used to measure the level directly. So you can look on page 23, and you can see like the float with the weight on the other side, and then connected to the pulley. I don't have the picture on there, but you can see where you're measuring that directly. Yeah. Page 23, last sentence before displacers. Electronic models attach an encoder to the pulley, which transmits its position to an instrument. Now, give me a picture of that. Displacers. So a displacer kind of works like a float, but a little bit differently. Like a float, your float's going to sit on top of the water. A displacer is going to go into the water, and however much water is in here, it's going to have, that displacer's got a certain amount of buoyancy that pushes up on the displacer and then changes the dial to percent based on how much that upward pressure there is. Flipping over to page 24, my only highlight for displacer is the first sentence of the first started paragraph. The operation of the displacer involves the raising and lowering of the liquid inside the standpipe. Indirect level measurement. So an indirect measurement would be for everything else, right? Our direct is like taking a tape measure or a ruler, seeing what the actual measurement is. But nobody in here can go stick their hand in the Mississippi and tell what the flow rate is in the Mississippi, right? You can't stick your hand like the surface of this desk and tell what the temperature of the desk is. So you have to take what's called an inferred measurement or an indirect measurement, which is getting one form of energy and changing it into another. So like we talked about thermocouples in the first section, what do thermocouples produce?
Like temperature to...
Y'all two probably won't know. What do thermocouples produce to measure temperature?
current.
Two dissimilar metals welded together on the end. Voltage. So they produce a millivolt signal that so that is an indirect measurement because you're taking voltage and you're turning it into temperature. So you're not directly measuring the temperature, you're measuring voltage, but then getting a temperature based on that. Does that make sense? So that is an indirect or inferred type of measurement. So 320 indirect level measurement, 321 the whole bottom left is highlighted. So first like 3 sentences. Measuring the levels of caustic liquids and acids poses special challenges. Using a measuring system that is equipped with components made of highly corrosive resistant materials that cost too much to be practical. Using an indirect method of level measurement, such as a magnetic float system, is one way to overcome this challenge. So, instead of having everything in a system that can withstand acid or whatever type of caustic acid or caustic liquid that's in here, they can put one float that's resistant to whatever that is. And like you can see, as the level goes up, this goes up, magnet goes up, and then once this gets so full and the magnet's up here, it's going to suck that magnet in and probably turn on a pump or a valve or something like that to empty the tank. Capacitive devices. You can use capacitance to measure level. Anybody remember what a capacitor is? What makes up a capacitor?
Power works. It's pretty much like a battery. You can hold power and then release it.
Sort of. So it's 2 plates separated by a dielectric. And based on those plates' movements or the separation of the plates by the dielectric, the capacitance will change. Okay? So on page 25, the first full sentence, that little middle paragraph, first sentence is highlighted. As the level in the tank increases, the capacitance between the probe and the tank wall decreases. So normally, a capacitor like you use on like your air conditioning system at your house, right? It's kind of shaped They're usually shaped something like that with little terminals at the top, or usually you have three terminals at the top, and then you have plates inside of here. And then in between that is the dielectric, right? So nothing is moving on this capacitor. It has a set capacitance, but the capacitance changes based on the dielectric in between getting larger or smaller, or I'm not going to talk about it too much, but you can use a capacitor to measure. You can have a load cell, capacitive load cell, because I could have a hook like this. It's got capacitor plate here and capacitor plate here with a dielectric in between. And then as I push force down on this, those capacitor plates get closer together and it changes the capacitance. And based on the capacitance, I can tell how much pressure is being applied to this. So capacitance changes based on the distance between the plates. Right? So, next highlight is the next paragraph, the sentence that splits the columns. Note that the probe is insulated from the process fluid when used in a conductive liquid. So, you can have these two pictures on the board. I have figure 28 highlighted. You're going to need to know that picture and know like the two different probes that are in there. I don't have that picture, but they're just measuring capacitance between the probes. But how these work, what are my two capacitor plates? Like you can see where my terminals are connected.
Yeah.
So one capacitor plate is the probe in the middle of the tank. The other capacitor plate is the tank wall itself. So you're turning the whole tank into a capacitor. What changes in a tank? The level. What is the level compared to in a capacitor? Like you have two plates and what? Pressure?
Dielectric.
Dielectric. Your level, or whatever your fluid is in here, is your dielectric. So your plates aren't moving. The dielectric is going up and down, and based on how much is in there, it changes the capacitance. Based on that, we can determine the level. Does that make sense? So you can have this one if you have a conductive liquid, you have to use an insulated inner probe. But if you're non-conductive, obviously you can use one that's not insulated. Does that make sense how these work? Pretty simple device, but pretty useful. Ultrasonic level measurement. 324. Flipping over to page 26. This is actually I think it'll be y'all's next lab that you're doing in the book. You're in the lab tomorrow. You're pretty much using ultrasonic waves to measure level. So it shoots ultrasonic waves down, bounces off the top of the water, bounces back. Based on how much time that takes, it can determine a level. Easy enough. First full paragraph on page 26, I got the second to last sentence highlighted. It is common to use ultrasonic devices to measure the thickness or thinness of solid objects or levels of solid materials in tanks or silos, such as grain or other agricultural products. So big grain silos, a lot of silos and stuff. You ever mess in any of the silos at Zattering's?
Yeah.
Do they have?
We were just at the bottom of them though. Yeah.
Do you know how they measure level in them? What device they use?
It's electronic or something like that.
Okay. So it could be a
Like we see it on a computer.
right, but it could be an ultrasonic level detector or
Oh.
something else.
Okay. What would the other one be? It's probably ultrasonic.
Pressure.
It could be pressure, but as big as their tanks are, I wouldn't think that would.
You know what we use, Jay?
It's probably all
We
that.
use ultrasonic.
Ultrasonic, yeah.
What was that last highlight?
Huh?
Where was it?
Full call just messed
First
with
full
two-
paragraph on page 26,
Okay.
second to last sentence, where it starts, it is common
Okay.
Don't really did.
agriculture.
The old one we have no pressure, like the one that's in assembly or extrusion, that's a pressure gauge.
They They just mess with the 3 up to 6 by us, and then I get the back, the factor. Yeah, I don't know what they did. They did something.
325. Excuse me. Radar detectors. I've got second paragraph, first 3 sentences are highlighted. GWR, which is guided wave radar, right? Yeah, guided wave radar. Units use a probe that typically extends to the bottom of the tank or vessel. The probe may be rigid or flexible. The device sends microwaves down the probe at the speed of light. So based on how fast that speed of light can go down and back up, they can determine the level based on that. That's one that I have not used, but I'm sure it's used quite a bit. 330 pressure-based level measurements. First sentence of 330 is highlighted. In many industrial applications, pressure measurements are used to determine level. What is the, Darren and Mark, what's the device called where you're measuring the level of that tank from the bottom? The little thing hanging off the bottom where you had to put like negative 3.6 as the bias in.
Yeah.
Okay, pressure, converting pressure to an analog signal.
Yeah. So pressure to an analog signal? P to
P to I,
yeah.
transducer.
Yeah.
So that's taking pressure in and outputting
Current.
a 4 to 20 milliamp signal.
Nice.
But that's using, I don't have any highlights in head pressure, but that's, think about the more pressure, the more water, the more liquid, the more whatever you put in a tank. It's going to put more and more pressure, and based on that pressure, we can determine a level. Level measurement and specific gravity. 332 on page 27, first sentence is highlighted. The relationship between pressure and level for substances other than water requires consideration of the specific gravity of the substance. The rest of that paragraph is a separate highlight. The specific gravity of a solid or liquid substance is the ratio of height of that substance to the weight of an equal volume of water. Water has been assigned a specific gravity of 1 since it is the standard to which all other substances are compared. Talking about specific gravity, water is what you compare everything to. The specific gravity of water is 1. Level calculations. They have level calculations are the, I have the equation highlighted. H equals P over 0.0360. So height is equal to pressure divided by
It's a weird number.
0.0360. So that is the formula for PSI per inches of height. So it's important to note that.
Yep.
That one is for inches. If you look down, there's another one for KPA, there's another one for PSI, and there's another one,
Yeah. PSI is per feet instead of inches.
oh, per feet,
Yeah.
and then the other one is KPA per meters.
Yeah.
Oh yeah. So you gotta watch, I could see them pulling other questions, just making sure you know the difference. They go through a bunch of probably every single one, using the different ones. I don't feel like those are super hard. That's one I don't care if you write in your Uglies book and use on the test. If you wanted to write those 4 equations, then we'll do it for you. 340 pressure-based level measuring devices. 341 hydrostatic head devices. I highlighted the heading of that, 341, along with the first sentence. Level can be accurately measured by determining the hydrostatic head pressure produced by a fluid and converting the pressure measurement to a height or depth. So that would be like what you're using on that trainer out there. A bubbler system, 342. First sentence of 342 is highlighted. A bubbler system uses hydrostatic head pressure to measure level in a tank. So how a bubbler works, if I had a tank like this, think of, so if I just had like a large size drink from McDonald's, right? If I had a straw and I didn't put it in there and I blew through that straw, it's gonna be pretty easy to blow through the straw, right?
Right.
If I have a full sweet tea from wherever, McDonald's or whatever, and I put it all the way to the bottom, and I blow in that, it's gonna be a little bit harder to blow air bubbles into the bottom of that. And maybe I drink half of it, it's gonna be a little bit easier to blow in that than it's gonna be with it full. So there's, based on the amount of back pressure that's put on this bubbler system, they can determine a height. Does that make sense? So this is good for areas like we used one of these. They were about to install one in a big tank that had it was very volatile. Like the pipe to the tank was a few feet up to fill the tank. So when it was pouring in there, like the top level of the tank was moving all around. We had floats in there, like just tied floats to the side. Those floats are constantly turning on and off, stuff like that. So if you have something where you have stuff that's moving around, you can use a bubbler system. A couple more highlights with this. Second to last paragraph, first two sentences are highlighted. On closed tank installations, the line connecting the differential pressure transmitter to the top of the tank is called a dry leg. It is used for installations in which the process vapors inside the tank are non-corrosive or non-plugging and are unlikely to condense in the line. Next paragraph, first sentence, is also highlighted. In applications in which the process vapors are corrosive or unstable, or the transmitter must be mounted at a lower level, the low pressure connection line should be filled with an inert liquid prior to calibrating or zeroing the transmitter's output. The low pressure line is then referred to as a wet leg. Page 30, the sentence that splits the columns and the one after it are highlighted as an online test question. The height of an accidental hole in the bubbler pipe is inversely proportional to the output of the level transmitter. In other words, the higher the hole is on the pipe, the lower the level indication for the tank. I wrote below that, pinholes are bad for bubblers. Online test question. Obviously, if that's letting air out somewhere where it shouldn't be, higher up, your reading is not going to be accurate. Pinholes are bad for bubblers. You got 5 questions on page 31. So you can knock those out real quick. All right, section 4. Last section is flow. So we did temperature, pressure, level. Now we're doing flow. Trade terms. I've got flow highlighted in the trade terms. The actual volume or mass of fluid that passes a given point per unit of time. So that would be like gallons per minute or liters per hour, something like that. It's amount over time. Multi-phase flow, I have highlighted. The simultaneous flow of materials that have different states or phases, solid, liquid, or gas, or have different chemical properties for the same state, e.g., or example, oil droplets in water. Primary phase is a continuous flow, the secondary phase are dispersed within the continuous flow. Page 33, we're going to talk about, why did not give me that picture? You can see the pictures in figure 33 where you have laminar, turbulent, and transitional flow. For a lot of flow meters, you need to have laminar flow, or else it's gonna mess up your flow meter, right? On on page 33, first full paragraph, first sentence is an online test question. Turbulent flow, as shown in B, is erratic instead of smooth or streamlined. So for you guys doing the trainer right here, if I had turbulent flow coming through that pipe, and you've got that paddle, like you saw the picture of the inside of that flow meter,
Yeah.
and it's just a little paddle wheel flow meter. If I had turbulent flow in there, that paddle wheel is not going to spin the same as it would if I had laminar flow flowing through it. So it's going to mess up my reading. So it's important to have laminar flow. Flow measure units. Before going to that, you can actually have, I don't have a picture. Picture in the top right of the page, you can have flow straighteners. So you can actually put those inside of a pipe and then get laminar flow on the back side of it. So they help. So if a lot of instruments, you either have to have a certain distance of pipe before the instruments, or you have to put a flow straightener in it. So if you can't have, like a lot of times it's like 6 or 8 feet of straight pipe with no turns before your instrument, or you could have 3 feet of pipe with a flow straightener and they'll work the same. Flow measurement units, 410, second sentence is highlighted. Velocity measures the rate of motion. Simply put, it refers to speed, the time it takes for a fluid to move a given distance. You'll have a question for volumetric flow rate. So I have the equation Q equals A over A times V in the top right highlighted. So that's just flow rate is equal to the area times velocity. Q equals A times V. We'll go through a couple example problems. Going on to page 34. Last paragraph before 420. The first sentence is highlighted. In summary, both volumetric and mass flow rate are related to how much fluid is moving over a given period of time. Out to the side of that, I wrote 2 basic ways of expressing fluid flow, or mass and volume. 2 basic ways of expressing fluid flow, or mass and volume. I'm going to write that out to the side of that.
Say it one more time.
2 basic ways of expressing fluid flow, or mass and volume. Differential pressure and flow relationship. So this is what the guy on Wednesday is going to talk a lot about, like differential pressure or pressure transducers. The whole first paragraph is highlighted, 420. Fluid flowing in a pipe exerts pressure in 2 different directions, as shown in figure 35. Pressure is exerted both in the direction of flow and against the walls of the pipe. These pressures measurements can be used to determine flow rate. So it's kind of weird to think that the pressure is pushing against the wall of the pipe, but you also think about if you popped a hole in the side of this pipe, water's going to be spewing out of that. So pressure is pushing, it's not just pushing horizontally, it's pushing against the sides of these pipes. Top right of the page, first sentence is highlighted. If a restriction is placed in the pipe, effectively making the pipe smaller, the velocity of fluid increases in the restricted area. They go through the equations for flow. So you have the square root of the measured differential pressure over the square root of the maximum differential pressure times the maximum flow. I don't have that highlighted, but they're going to go through that to find, that's what the device is going to be doing for you, is the square root function of flow. Right after that equation, I have the first sentence of that next paragraph highlighted. As the formula shows, the flow equals the square root of the measured differential pressure divided by the square root of the maximum differential pressure multiplied by the maximum volumetric flow. page 35. 430 differential pressure flow measuring devices, orifice plates. Everybody remember me talking about orifice plates last time?
So that,
Definitely for you guys that have done P-Tech, you should know what an orifice plate is.
that should work the same way as making the pipe smaller, right? To raise the velocity.
That's what this does.
Okay, so it's
It
raising the
works
velocity.
exactly the same way,
Okay.
because that's what, so this is different ways of making the pipe smaller.
Right.
So, you take one of these orifice plates and you put it between two flanges, and you have a very, very, very known opening or orifice in this plate. And based on that, math can be done, like the square root can be done, usually done inside a differential pressure transmitter.
That should also reduce the exerted pressure, right? From the other side.
So differential pressure, you put that inside of a pipe, and then is that my I don't show. So this would be like flow through an orifice plate. So my pressure on this side is lower or higher.
On that side?
Lower.
If my flow is coming in from the left and going to the right, and I put an orifice plate in, is that going to cause the pressure here to be higher or lower than the pressure here?
Higher.
Higher, because it's going to all that pressure is hitting, not hitting a wall, but it's going to be like going through a smaller orifice. So I put my high pressure tap on this side of my orifice plate, and then I put my low pressure tap on this side. And based on the size of the pipe, the orifice, and the math, you can determine a flow based on that. Like it's pretty.
Yeah, it's kind of like.
It's very simple, but it's also like there's a lot of math that goes into it. But it's not like we're never having to do the math. Like the square root extractors are built into the differential pressure meters. Does that make sense?
Yeah.
Like you are creating a known disturbance.
Right.
You are, and based on that, you are determining the flow,
Right.
which is how most flow meters work. So you got orifice plates. You should know what those are. They all have calibrated, very calibrated openings. You can have like the eccentric or segmental, which is it's not directly in the middle. It's not directly a circle. I have never seen those ever. I've only seen regular orifice plates, in my experience.
Yeah, I've never seen those two small.
No, I haven't. So, well, you'll be using an orifice plate on that trainer, like it's the last lab for that trainer right outside the door. Flow nozzles, 432. So, same thing, but different. So, 432, second paragraph of flow nozzles, first sentence is an online test question. Flow nozzles are more accurate, but more expensive than orifice plates. Which makes sense, right? There's a lot more going on here than just a hole in the pipe or a hole in a plate. These are more expensive. Orifice plates are used because they're cheap and they're easy to change out. They're easy to get, stuff like that. This is going to be more expensive. You need to have figure 37 highlighted as an online test question. You need to know what a flow nozzle looks like. So you can see by looking up on the board at your picture, like the taps aren't directly right next to the flow nozzle itself. Your upstream tap, which is going to be your high or low.
The upstream will be high.
Upstream will be high. This will be your low stream tap. You plug these into the differential pressure transmitter, and based on that, you can get a flow rate. Venturi tubes, 433. This is another one that you will do in that lab. I have a Venturi tube. So this it's not a direct like a super reduction in the middle right here, or like with your orifice plate, it's not a immediate reduction. They actually it's like a tapered reduction in here, and your pressure taps are going to be in a little bit different place. The low pressure tap is going to be directly in the throat, and then the high pressure tap is going to be all the way to the other side, all the way to the high pressure side. In Venturi tubes 433, the sentence that splits the columns is highlighted. Venturi tubes are the most accurate of the restriction type flow devices. And I can't remember if I taught it to y'all, if I taught it to another class, but anytime there's like a restriction or like disturbance in the process where you have to get a reading based on that, that is called loading. So loading would be like how much disturbance this orifice plate causes, or how much disturbance this flow nozzle causes. The pretty sure this is accurate. The venturi tube of the restriction type devices causes the least amount of loading or the least amount of disturbance because it's kind of like a gradual change, right? Like I can flow more, and the water's not going to get as turbulent and stuff like that through this pipe as it would through like an orifice plate one. Pidot tubes. So that's the third one that you'll be using in the lab. So I've got an orifice plate, a venturi tube, and a pidot tube. 434. On page 37, 434, second sentence is highlighted. A pidot tube can also be used in to measure flowing liquids that are not confined in a pipe or duct, such as the flow of water in a river. So you kind of have two different openings in this. Like they have a calibrated opening in the very center, which you're going to have your high pressure tap, and your low pressure tap will be behind it, with everything else, with the water that's just around it. So they make these to where you can throw them out in the river and stuff like that. You can probably go on some website and see what the flow of the Mississippi is right now. That's because there's probably one of these out in the water somewhere that the National Weather Service or whoever is probably, what's the name of the other weather service or Weather Channel gets all their stuff from? NOAA, NOAA. NOAA does all their, like NOAA is the one that does a lot of this stuff, or like the stuff out in the Gulf. The tour sucks now. We used to be able to go do a tour of Stennis Space Center out in Mississippi. And they used to like drive you around and you could see where they were strapping bolting the rocket engines onto the stands.
Nice.
But that whole, thousands of acre facility, NOAA also operated out there, and they had like a 5-story building that they could fill with water and do like different tests on their. They use like big giant buoys, like I don't know, probably 8 foot in diameter at least, that they put out in the Gulf and stuff like that. And that's where we get our information for like hurricanes and shit like that. Like that stuff NOAA puts out in the Gulf, and then they're just data collectors. So that has nothing to do with this. Page 38. Other types of flow measuring devices, 444. You can have target flow meters. Second sentence of 441 is highlighted. The electronic or pneumatic output produced by the target flow meter is proportional to how much the plate is deflected by the impact of the fluid flow. So obviously, put a target in here, however much fluid is pushing against that plate, it can connect to like a bellows device and determine a flow based on that. Pretty simple device. Electromagnetic flow meters. These are pretty cool. I have never seen one of these. I thought they had. They do. Like they have not a picture of one, but a picture of how it works. In electromagnetic flow meters, 442, right hand side of the page. Third sentence on the right hand side of the page, 38 is highlighted. One major limitation with electromagnetic flow meters is that the fluid must be electrically conductive, which means the device cannot be used with gas. So most liquid is conductive, right? You can go outside with an extension cord on the ground that has a fray in it. You have wet ground and you're on your bare feet, you're going to get shot.
Yep.
Water is conductive for electricity.
Most
Gas.
oils tend not to be.
What's that?
Most oils tend
Most
not to
oil tends not to be, but there's probably still some type of like.
be. Right. Unless it's like mineral
There's
oil.
probably still some type of constant that can be put into this to measure it. Probably not. I think most like the liquid hydrocarbons that like the refineries and stuff use, like they're using orifice plates. That stuff. What's the advantage? This isn't a good picture of one, but what would be you think would be the advantage to electromagnetic flow meter? It's hard to tell. There's no loading. There's no like the pipe is just straight through all the pieces of this on the outside of the pipe, right? So there's no loading. What's the disadvantage of this compared to an orifice plate?
Heat, temperature, and probably.
Maybe, but like the biggest. Why would you use an orifice plate over a magnetic flow meter?
It's cheaper.
Orifice plate is way cheaper than a magnetic flow meter. Way cheaper.
Yeah, way
thousands and thousands and thousands of dollars cheaper. Turbine flow meters. Pretty obvious how these work. 443, first two sentences are an online test question. In a turbine flow meter, figure 42, the moving fluid turns the blades of the rotor in the device. The speed of rotation of the turbine rotor is proportional to the flow rate. So this just has a magnetic pickup on here that senses the blades, right? So what kind of, anybody know what kind of signal this would output? This is probably too hard. It would be a sinusoidal signal, which all that means, like everybody knows what I'm talking about. It would be like that.
Yeah.
Right? Just be a sine wave. Right? Because like at my 0 points right here where I don't have, that's where this blade, instead of being like that, would be like this. So I would have the least amount of induction between the two, and then when it's like this, it would be either at its highest or lowest point. Does that kind of make sense? Second paragraph, second sentence is also an online test question. Turbine flow meters are suitable for use at any pressure and extremely high and low temperatures. Good to know. Variable area flow meters, 445 on page 39, first sentence is highlighted. Variable area flow meters use the position of a float, piston, or vane in a tube to indicate flow rate of a gas or liquid based on variations in the size of the area through which the fluid flows. So, flipping over to the next page, that would be like this. So Darren and Mark, what is this? Looks just like the very close.
The flow meter.
Flow meter, what do you call it? Starts with an R. Rotometer. Good. So this would be just like you had a float in here, and based on how much pressure is pushing on the bottom, it can determine a flow rate. Right? First sentence on page 40 is highlighted. I have a couple of questions come off of that. A rotometer is a vertical tapered glass tube that contains a float. You need to know that is a type of variable area flow meter. So based on how much area that the largest part has, or this is a little bit different than the one out there, but how much area is down here, they can determine a level based on that. Coreless flow meters, I don't think I have highlights on that. I don't have highlights, but you can actually, it's kind of interesting how they work. So you can have motion sensors on either side, and if you put a pressure on this, there is a physical change in the tube. And based on that change, they can determine a flow. I've never worked on, or anything one of these, but it is kind of cool how they work. But nothing highlighting that. So that is all my highlights for this chapter.